Welcome to another video. I'm recovering from sickness, and so I'm just gonna wing this. It says explain all membranes, pressures, mechanisms that make negative pressure ventilation possible. Alrighty. And so we're gonna fly over here to the membranes. We have our parietal pleura, we have our pleural space, our visceral pleura. We also have these things called elastin, and we have surface tension from H2O in the alveolus. So when volume increases, pressure is decreasing. Then it's suction, which means air is flowing in. So the more negative it gets, that's when the lung starts to increase in size. And it is filled with air. Membranes, pressures, mechanisms that make. Yeah. Alright, describe what pneumothorax is and how it occurs. Pneumothorax is when air gets in the thorax. It's caused by a hole in the lung by either being punctured in some way or another. So that's what pneumothorax is. Pretty basic. Next up, what is surfactant? How does a lack of surfactant impair ventilation? So we're going to scroll down here to our little surfactants. I blew this up somewhere, right down here. So here we have our H2O molecules. Our H2O molecules are going to create hydrogen bonds with each other. So those hydrogen bonds are going to create surface tension. As they create surface tension, they're going to start to collapse this alveoli, which is bad for us because then we can't inhale as much. But luckily, we have these little surfactants. These surfactants are produced by pneumocyte type 2s. And what they do is they break up the surface tension by disrupting those hydrogen bonds that form between water molecules, decreasing surface tension. And so as we see in Laplace's law here, the pressure equals the 2 times the tension divided by the radius. So a smaller radius is larger pressure. A smaller tension is smaller pressure. So if you have more surface tension, you have less surfactants, more surface tension, you have an increase in pressure. If you have a smaller radius, boop, you're going to have an increase in pressure. And the inverse is true. Alrighty. Talked a little bit about surfactants. Also, fun fact, fetuses don't produce surfactants until the stress is on the baby, hypoxia. So then the baby's like, oh, I actually need to breathe on my own. So it starts to produce surfactants after that stress hormone is released from hypoxia. Next up, in discussion, explain surface tension. Oh, I guess I did a little of that. And the role of Laplace's law. Oh, I guess I did that. Right on. Did that already. Next up, explain the alveolar gas equation and how it can be used clinically. Alrighty, where's the FiO2? So, this is the alveolar gas equation. This is a percentage Excuse me, sorry, jeez Louise. So the FiO2 is the percentage of oxygen. And then you have your atmospheric oxygen, the pressure of the atmosphere. Then you have pressure of water vapor, and then water in your lungs. And then you have pressure of partial pressure CO2, and then you have your respiratory exchange ratio. With these things is if you are put on a oxygen machine, that's going to increase your O2 intake, and so that will mean that your alveolar oxygen will increase. If whenever you figure that out, that PaO2 is the pressure needed to force oxygen in the blood. So if it's high, the oxygen doesn't want to diffuse into the blood as much, and so it's harder. So you want to decrease that, so that way blood can get in there easier. Oxygen, sorry. And then, and then you have with your R is basically just your CO2, the volume of CO2 over the volume of oxygen. And so it's usually 0.85 whenever you're resting. If you burn more fat, it's 0.75. If you burn more sugar, it's 1. And so that's what makes up the alveolar oxygen equation. A nice thing to know about that is PaO2 only needs to go through about a third of the alveoli to get to 102, so that's pretty nice. Next up, it says, discuss how CO2 and O2 are transported in the blood. Include a description of the hemoglobin dissociation curves and the affinity for hemoglobin for oxygen, and how do they affect the association curve. So we can go back to over here a little bit. So oxygen is introduced into the blood by overcoming that alveolar pressure. And then once it's into the blood, and then carbon dioxide is done a similar way. And then every time an oxygen is moved, like that one moving out, another oxygen will come take its place. And it'll be burned in either some sort of metabolic process or used throughout the body. And then oxygen is carried throughout the body through hemoglobin. Hemoglobin binds 4 oxygen molecules, I should say, and then transports them throughout the body, and it takes them other places. Hemoglobin also carries some CO2, which we'll get there in just a second. Let me fly us over there. So with your CO2, whenever it comes across, 23% of it is going to bind to hemoglobin, 7% of it is going to dissolve into the blood, and 70% is going to be made into bicarbonate. That's where your majority of it is. So that is how they're transported in the blood, how they get where they're going. Alrighty, next it says include a description of the oxygen hemoglobin dissociation curve and factors that influence the affinity. So here we are. So black here is our normal. What it's saying is we have our hemoglobin saturation per oxygen. Actually, I'm going to double check that one real fast. Excuse me, don't mind me as I go back to my original. Yeah, it's right. So, so it's your hemoglobin saturation over your oxygen. Oh, now I can't erase those. That's okay. And so whenever oxygen levels increase, it binds more to hemoglobin and more and more and more until it's reached the amount that it can. Now, let's say, and some factors that affect this are temperature, 2,3 BPG, carbon dioxide, hydrogen ions, and pH. So if you increase any one of those, you're going to shift your dissociation curve to the right. If you decrease any one of those, you're going to shift it to the left. And so with that being said, that's because these things are causing oxygen to be kicked off more, and so it's not bound to hemoglobin. While these things are, the decrease is allowing it to be kicked off less, meaning be bound to hemoglobin more. And let me show you real quick what that means of being bound to it or not. So there's an R state of hemoglobin, which is when the hemoglobin is oxygenated, has all those oxygens. And there's a T state, creates this little boop. Nope, sorry, that's whenever it's oxygenated, it has a boop. Whenever it doesn't have the boop, it's flat. That means no oxygen can bind, which means that it kicks off the oxygen if it's forced into that state. And so the CO2, H plus, CO2, H plus, 2,3 BPG will all be kicking this thing off, so that way oxygen can be released. And that's the end of my video. I'm sorry I'm sick, but hope you enjoyed some of it at least. Bye.